Welcome to this next section of the Electromagnetism modulate milestone. In this sixth section, finally we will move towards the magnetic field, and we will be discussing the magnetic force, the Lorentz force, and we will be also going into the Gauss law for magnetism. So again, with going to the history, we could go back to the 13th century with the Chinese and Arabics and Indian. I'm not really going to do that, and then we will then move to Ørsted and Faraday and Henry in the 19th century, and then in the 20th century, Maxwell unites electricity and magnetism into one big theory, the electromagnetism. And then if you want to go again towards the modern description of electromagnetism, then we would need to have a QED, quantum electrodynamics, which was really discovered by Feynman and Schwinger and Dyson in the 20th century. And then there was a further unification of the electromagnetic fields with the weak force, which was done by Lambert and Salomon and Gresham in the late 20th century. And after that, there was, the inclusion of the Higgs boson to the final picture. And that's essentially our understanding of the particle physics. So, about magnetic fields, well, what you usually think of is that you have a bar magnet, and that creates a permanent magnetic field, and this is symbolically denoted with the letter B, which is just because the letter A was used for something else, and Maxwell just went in order in the alphabet. And it's a vector, so it's going to be a vector field. And we can use like magnetic material, like iron, to look at the magnetic field lines. Similarly, what we saw earlier with the electric field lines. So in the bar magnet, we have a north and a south pole, and they act like if they are a dipole. So the field lines look very, very similar to the electric field lines of the electric dipoles. And as you put two magnets with opposite poles next to each other, as you could see it in the second picture, then you see something that almost like what we saw with the capacitors electric field, and then there is a force, attractive force there, and you rotate the bar magnet, so the north pole is against the north pole, then there is a repulsion between the two things, and this is how the magnetic field lines look like. So then going into the magnetic force, similarly that we discussed electric fields and then electric forces, the magnetic force is called the Lorentz force, and it is proportional to the charge of the particle, denoted with Q. And when you have a negative charge, it is directed opposite to the force on the positive charge, moving in the same direction. And then when you have a magnetic field, then this magnetic force is proportional to the magnitude of this magnetic field vector B, and it's also proportional to the speed of the particle, denoted with V. And if this velocity vector makes an angle, let's call it U, with the magnetic field, then the magnitude of the magnetic force will be proportional to the sine of this U. And so if the particle is moving parallel to the magnetic field, then the magnetic force will be 0. And if it is moving, perpendicular, then it is the maximal. And so these observations can be summarized in a compact way by including the cross product of vectors. So the force is going to be this charge factor times the v, the velocity, cross the b, the magnetic field vector. So this is where the right hand rule comes in. So if you put your finger with the F, then your pointing finger will be the V, and then your middle finger is going to be the B vector. So that's how you get the magnetic field direction. So here you go, B, you have F here, V, and B here, this you can do with your left hand, but you can do with your right hand. Then going into the unit, so if we want to express B from this expression, then we divide the velocity and the charge. So we get that it's Newton over coulombs times meter per second, and then realizing that that is coulombs over seconds is amperes, this is going to be Newton per ampere meter. So let's just say that we have a uniform magnetic field, which is showing towards us out of the screen, and we put a particle going in. Then every time the particle will, you try to imagine this with your right hand. So there is the magnetic field in one direction, and then we push it in from the top. Then applying the Lorentz force direction, there will be a force which is towards one point, and so this every time you go, there is going to be this centripetal force, and so your particle is going to go around the circle. And so if you do the same thing in 3 dimensions, then this is going to be a helix. But let's just stay with the 2-dimensional part where you are going in a circle, so you have a centripetal acceleration. And so from our mechanic studies, we know that centripetal acceleration or the centripetal force can be calculated as the mass of the particle times the velocity squared over the radius of this circle that the particle takes. So we can put these two together, and because it's the same force, and from this we can express that this radius of the circle is going to be mv, which is essentially the momentum of the particle divided with the charge and the magnetic field. And so this actually is how synchrotrons particle accelerators work. So you fix your magnetic field usually, and then if you want to have your particle to go faster, then that means that you have to increase the radius. So that's the reason why we have this bigger and bigger. That's kind of the reason why we have these bigger and bigger accelerators. The LHCs, 37-kilometer long one. Earlier they were much smaller, and then in the future they plan to do 100-kilometer long accelerators. But this whole thing can be also actually used for figuring out that you have some new particle created at the detectors, and you are interested in the momentum of that, so that's unknown. You don't know the particle, but you do know the magnetic field, and you know the charge. So by measuring the radius, if you're measuring the curvature of your particle, then you can figure out the momentum of the particle. So I was mentioning in 3D, this is going to be a helical path, on a helix, and so the angular speed of the particle is what we call the synchrotron frequency. As I mentioned earlier, that synchrotrons are used for this. So that is defined to be the velocity of the particle divided by the radius. So by just including what we learned earlier and dividing with the r, you get that this synchrotron frequency is charge times the magnetic field divided with the mass of the particle. And we can also look at the time it takes to go back to the same spot. So that is going to be a very similar formula, but we include a 2 pi. And so that leads to the inverse with the 2 pi of the angular frequency is this t. And so we calculate that to be 2 pi m divided with the q and the b. So there are lots of examples with this. So let's just look at this problem where you have a proton. So that means that you know the mass of the particle, right? You can go to Wikipedia or any other source and check what is the mass of the proton. It's moving in this circular orbit. We know what is the radius, 14 centimeter. So don't forget to change that to meters. And then we put it into a uniform magnetic field, which has this 0.35 Tesla magnetic field. So I actually didn't think, as I mentioned this a second ago, that the unit which we discussed earlier to be the Newton over ampere meter, is defined to be 1 Tesla. And 1 Tesla is actually a very big number. So, the planet's magnetic field is like thousands of, it's not 1,000th of a Tesla. So, when you go to these MRI objects and at the hospital to check your brain and these things, so those use about 3 Tesla magnets. CMS detector at CERN that I'm working on has a 3.8 Tesla magnet, which is supposed to be one of the biggest magnets around. And so this 0.3 is also kind of big magnetic field. We also know the direction of this particle, but actually the direction of the magnetic field is perpendicular to the velocity of the proton, and so we are interested in the speed of the proton. So to solve this, make a drawing, and then we have the formula from the previous slide, change your units, and then check the answer in the end if that makes sense. For example, the particle here should not really go faster than the speed of light, right? That's a good check. Applications, I already mentioned one with the MRI, for mathematical checks, and I also mentioned the applications for particle accelerators and particle detection. There is another one which is used for chemists and also physicists. This is this so-called mass spectroscopy or mass spectrometer, in which we, in this formula earlier, we need to have a velocity of the particle. So we use a capacitor, which then creates an electric field to accelerate your incoming ions or particles that will now have an initial speed, and then we lead this into a magnetic field, and so because of the Lorentz force, there will be a curvature on this particle, and then we measure where we put some detector, and we measure where this particle ends up in the end. So then we have the radius of this circle, and based on that you can figure out what was the mass of the particle. So the chemists use this to figure out what kind of material they are dealing with. You can have some unknown thing, CSI. There was, in these movies you have that they have these materials, they don't know what it is, so they kind of put it into here. They break the material down into ions. So that's the particle here, and they push it through this electric field, and then push it through the magnetic field, and measure the radius, and figure out that this ion, had the atomic mass of sodium. So that ion was a sodium ion. Or when you go to fundamental physics, this is the same thing that you find that this is the whatever particle there. It was a proton or something like that. Okay, so far we have been discussing only one Gauss, one Maxwell law, which is the first law of Maxwell, which is the Gauss law for the electromagnetism. We can do the same thing now for the magnetic part. So earlier I wanted to say that we did this law for the electric fields, and now we are going to do it for the magnetic fields. So we can similarly define a magnetic flux. Now we will call that phi b, and again this is going to be the perpendicular part of the magnetic field with some surface, or that you get by the cosine, which essentially mathematically is a surface integral. So that means a vector product, not a vector product, it's a scalar product between the two vectors of the magnetic field and the surface vector, which is perpendicular to the surface and has the magnitude of the surface area. So the unit for this is Weber, and that means Tesla times meter squared. And so now we can get into, doing the same kind of tricks that we did earlier, and we find that the magnetic flux is always zero. So whenever you connect your magnetic field with a Gaussian surface, that will lead to zero. And so the meaning of this is that, well, okay, maybe let's step one back and say that the meaning for the Gauss law for electricity was that the source of the electric field is the charge. When you have a charge, that will create an electric field. So here, when we say that this is zero, that means that the magnetic field is sourceless. So there is no such a thing as something that is similar to the charge. So there is no single north pole, or there is no single south pole. These things only exist as a dipole kind of system, the two of them together. And so that's what Maxwell said. This is the second law of Maxwell and the Gauss law for magnetism. In words, the total flux through a closed surface is always zero. And so this is a lie. This must be a lie. This sentence must be wrong. If this was not, if it was true, that would mean that there is no reason why all the electrons, all the particles have the multiple charge of the electron. In order to fix the charge of the electron, or the charge of anything to be the multiple of the electron, we need at least one so-called magnetic monopole to exist in the universe. All the modern theories, string theory and whatever you're thinking of, assume that there exists a magnetic monopole. However, we have not found it yet. There has been a lot of research done for this, and I will have a presentation about this specifically. This is not really part of this module, because in this module we learn about electromagnetism as of Maxwell. So based on that, this is zero, and based on the other new theories that are not proven yet, but otherwise it's very hard to argue for the charge of the electron. Then this is something beyond this module, and so it's part of a different presentation, or we can just chat about this at the session time. That's all for today. Please give your comments in the comment section and like the video. Bye bye.